PCR presented by مريم عمر الخطاب محمد. Introduction. PCR is a method for in vitro amplification of DNA. It has substantially accelerated the pace of research in many fields of biology, both by reducing the time required to perform routine manipulations of DNA and by making new manipulations possible. The technique is based on the following. DNA can be denatured from a double-stranded molecule to a single-stranded molecule by heat. When the single-stranded DNA molecules are cooled, they anneal to a double strand. The process of two single-stranded DNA molecules annealing occur with high fidelity. A always pairs with T and C with G. Subsequently, the template DNA is denatured by heating. Specific primers designed for the sequence of insert anneal on the corresponding DNA sequence of the template DNA when the reaction is cooled. DNA polymerase extend the DNA from 50 to 30, building a mirror image of the template strand. At the end of one cycle, two exact copies of template DNA have been formed. Using this technique, DNA can be amplified exponentially. This allows minute amount of DNA from biological samples to be assayed, making the technique extremely powerful for basic science and clinical research. In essence, PCR is multiple rounds of primer extension reactions, in which complementary strands of a defined region of DNA molecule are simultaneously synthesized by a thermostable DNA polymerase. During repeated rounds of these reactions, the number of newly synthesized DNA strands increases exponentially, so that after 20 to 30 reaction cycles, the initial template DNA will have been replicated several million-fold. This power is faithfully amplified along the low cost and simplicity of the method have made PCR an indispensable tool. Parameters influencing the yield and specificity of PCR. Number 1. DNA polymerase. Many thermostable DNA polymerases are now commercially available, each with different characteristics of thermal stability, exonuclease activity, processivity, fidelity, and reverse transcriptase activity. Taq DNA polymerase, with its heat stability, high optimal temperature, and broad pH tolerance, is the most widely used thermostable DNA polymerase. The recommended concentration range of Taq DNA polymerase is between 1 and 2.5 units per 100 reaction. Enzyme requirements may vary with respect to individual target templates, primers, and suppliers. Taq DNA polymerase from different suppliers may behave differently because of different formulations, assays conditions, and unit definitions, especially for non-licensed products. If the enzyme concentration is too high, more than 4 units per milliliter, non-specific background product may accumulate. If it's too low, an insufficient amount of desired product is made. Number 2. PCR buffer. Each thermostable polymerase has unique buffer requirements for optimal activity, most requiring TrCl between 10 millimolar and 50 millimolar at pH 8.3 and 9. A stabilizing protein such as PSA or gelatin, and a non-ionic detergent such as tween TM20, NB40, or Triton TMX100 is also usually required. Concentrated reaction buffers are normally provided by the supplier of the enzyme, but for certain applications, other additives such as furamide or glycerol may be essential for an efficient reaction. Number 3. Magnesium concentration. Magnesium concentration has a significant effect on the efficacy and specificity of the PCR reaction. In addition of its direct influence on enzyme activity and fidelity, magnesium also affects the Tm of the various hybrids that form during cycling, including primer-template, template-template, and the primer-primer. If the magnesium concentration is too low, little or no product may be produced. If it is too high, artifactual products may result from non-specific priming of template DNA or from primer dimers. For each new primer pair, it is generally worthwhile to titrate the magnesium concentration in 0.5 millimolar steps over the range of 0.5 millimolar to 5 millimolar. It is also important to remember that free nucleotides and any additive present in the reaction influences the effective magnesium concentration. Number 4. DNTPs. A total DNTP concentration between 80 millimolar and 800 millimolar, 20 millimolar to 200 millimolar each DNTP is recommended for most PCR reactions. It is tempting to believe that more is better, but it should be recognized that 5 microgram of PCR product can be synthesized from only 15 nmoles of DNTP. Concentrations higher than 800 millimolar increase the rate at which Taq DNA polymerase misincorporates nucleotides. This effect can be exploited to generate mutant, but should usually be avoided. Number 5. Template. In some respects, the quality of template DNA is not as critical for PCR as it is for certain other enzymatic manipulations. Evidence for this can be found in the wide variety of sources of DNA that can be successfully amplified, including fossil DNA, entire bacterial colonies, paraffin-embedded tissue, and single human hairs. For some applications, however, the quality of the DNA template is a very important factor. For example, amplification of long pieces of DNA requires that the template be prepared in such a way as to minimize a single strand length, and a GC-rich template may require higher or prolonged denaturation steps and the use of a more thermostable polymerase. A 10 to the power of 7-fold excess of primer to template is a good rule of thumb for a standard PCR reaction, because primer concentrations above about 0.5 millimolar can result in a determinantal amount of primer-dimer formation. The concentration of a template DNA is limited to about 50 fm. For a 100 microliter reaction, this concentration represents picogram amounts of plasmid DNA, nanogram amounts of bacterial DNA, and microgram amounts of human genomic DNA. Under specific reaction conditions, however, genomic DNA from a single cell can be amplified. Number 6. Cycle parameters. It is critical that complete strand separation occurs during the denaturing step. A temperature of 94 to 96 degrees Celsius for 1 minute is usually sufficient, but GC-rich templates may require a higher temperature. It is thus usually several degrees higher from than the calculated Tm for the primer template. The extension reaction is fairly temperature tolerant, and 72 degrees Celsius is optimal for many thermostable polymerases. The duration of the extension step should be adjusted for the length of the amplified region, with 1 minute recommended for targets less than 500 base pair in length and 2 to 3 minutes for targets greater than 500 base pair. To reduce the chance of mispriming that may result from a non-specific hybridization occurring during the addition reaction component, so called hot start PCR, in which tag DNA polymerase is added only after the other reactant are raised to a temperature of 70 to 80 degrees Celsius may be recommended. Due to the high molar excess of primer to template, the optimal annealing temperature is dependent on the rate of cooling from the denaturing temperature. Number 7. Primer design and concentration. Primers from 10 to 30 nucleotides in length with a GC composition of 40 to 60% are used in most PCR reactions. Obviously, self-complementarity and complementarity between primer should be avoided, as should continuous runs on the same nucleotide. Primers corresponding to regions of the template containing a high degree of potential secondary structure should be also avoided. Specificity and efficacy of their action is in many cases improved if the free end of each primer terminates in 2 or more G or C residues. Due to the increased likelihood of mispriming, however, it is best to avoid an unusually high GC content at the free end of the primer. Many applications depend on the use of primers incorporating special features in their design, either to control specificity or to facilitate subsequent manipulations of the amplified product. These features may include modified nucleotides or non-complementary sequence. Primer concentrations between 0.1 molar and 0.5 millimolar are generally recommended. Higher primer concentrations may promote mispriming and accumulation of non-specific product, as well as increase the probability of generating a template-independent artifact, primer-dimer. These side products are themselves substrate for PCR and compete with the desired product for enzyme DNTPs, and primers, resulting in lower yield of the desired fragment. Detection and imaging of PCR products. Nucleic acids don't absorb light in the range of wavelengths to which the human eye is sensitive, and so cannot be visualized directly. A number of indirect methods have been employed to detect nucleic acids following electrophoresis, both within gels and on the surface of membranes after their transfer from gels. The most common way of detecting nucleic acids in gels is fluorescent dyes. Fluorescent dyes, where sensitivity is not of utmost importance. Detection of nucleic acids using fluorescent dyes has traditionally been the method of choice, its chief virtues being its simplicity and speed. The dye is in many cases simply added to the gel and electrophoresis buffer, so staining takes place during electrophoresis. After the separation is complete, the gel is exposed to light of a suitable wavelength. The light emitted by the dye molecules is either viewed directly or captured by some sort of image recording device. As in all fluorescent events, the light emitted by the dye is of a longer wavelength than that used to excite the dye. Optical filters can be used to prevent light of the existing wavelengths from entering the imaging system, thereby improving sensitivity. The dye DNA complex often exhibits enhanced fluorescence relative to the unbounded dye, a property of the dye that also leads to greater sensitivity. In recent years, the development of more sensitive fluorescent dyes has been spurred by the rising cost associated with handling radio-labeled nucleic acids. There have also been improvements in imaging devices. Whereas using photographic film in an ultraviolet light box was previously the only way to record the images of fluorescently stained gels. Charge coupled device CCD cameras now offer greater sensitivity than film, and a number of very sensitive dedicated fluorescent imagers are also available. A serious objection to the use of fluorescent dyes for nucleic acid detection is that they represent a safety hazard and must be handled and disposed of accordingly. It should come as no surprise that molecules exhibiting a high affinity for DNA should have the potential to interfere with DNA function. Most dyes used for detecting nucleic acids are mutagens and are either suspected or confirmed carcinogens. Because it is simple to use and is sufficiently sensitive for most routine procedures, sodium bromide has long been the standard fluorescent dye for staining nucleic acids in gels. Agarose gels are most conveniently cast and run with buffers already containing the dye at a concentration of 0.5 microgram per milliliter. Ethidium bromide is an intercalating dye. The planar molecule fits with high affinity between adjacent base pairs in the double helix of double-stranded DNA, but it also binds single-stranded DNA and RNA. If dye is included in the gel and running buffer, the progress of separation can be monitored during electrophoresis by using a handheld UV lamp, but sodium bromide stain gel are most commonly viewed by placing them on an ultraviolet light box. The image can be recorded using either a conventional or a CCD camera. Spectrophotometric quantification of nucleic acids. Due to their molecular structures, nucleic acids absorb light of certain wavelengths. For both DNA and RNA, maximal absorption occurs at 260 nanometer. Over a wide range of concentrations, a linear relationship exists between the absorption of light and the nucleic acid concentration. Inside a spectrophotometer, the sample is exposed to ultraviolet light at 260 nanometer, and a photodetector measures the light that passes through the sample. The more light absorbed by the sample, the higher the nucleic acid concentration in the sample. The amount of light absorbed by a nucleic acid is a function of the molar extinction coefficients of the substituent nucleotide bases. The Pearl-Lambert law relates the amount of light absorbed at a given wavelength to the molar extinction coefficient and concentration of an absorbing molecule. A equals E times C times L, where A is absorbance, E is the molar extinction coefficient, C is the concentration of the solute, and L is the length of the light path in solution measured in centimeters, usually 1 centimeter. By entering the molar extinction coefficient in molar to the power of -1, centimeter to the power of -1, concentration is obtained in mole per liter. Alternatively, by entering the specific absorption coefficient in microgram per milliliter to the power of -1, centimeter to the power of -1, concentration is expressed in microgram per milliliter. Assuming the cuvette has a path length of 1 centimeter, different nucleic acids are characterized by the following specific absorption coefficients. Single-stranded DNA 0.027 microgram per milliliter to the power of -1 centimeter to the power of -1. Double-stranded DNA 0.020 microgram per milliliter to the power of -1 centimeter to the power of -1. Single-stranded RNA 0.025 microgram per milliliter to the power of -1 centimeter to the power of -1. By entering these values into the Beer-Lambert equation, an absorbance at 260 nanometer of 1.0 corresponds to single-stranded DNA 37 microgram per milliliter, double-stranded DNA 50 microgram per milliliter, single-stranded RNA 40 microgram per milliliter. For single-strand DNA, this conversion factor applies only to longer nucleic acid molecules. For oligonucleotides, an absorbance of 1 corresponds to concentration of 20 to 33 microgram per milliliter, depending on the oligonucleotide length and base composition. The following formula provides an estimate of the concentration where N equals length in bases. C picomole per microliter equal absorption 260 divides 10 times N. A more accurate formula accounts for base composition as well as length. C b-mole per microliter equals A 260 divides 100 divide 1.5 Na plus 0.71 Nc plus 1.2 Ng plus 0.84 Nt, where N equals number of each of the 4 bases A, C, G, and T. Thank you.